Alright, welcome to the third tutorial in the series of tutorials explaining how to create a SlopeBlend effect in CryEngine. So we're coming off of where we left off in the last tutorial. We defined all of the parameters and texture slots and features that we want and need for this effect. So I'm just going to kind of jump straight into the next part, which is actually calculating the SlopeBlend effect. So I'm going to create a new section here, a new commented section, and we're going to call this generate SlopeBlend mask. And we're going to create a function that returns a half. Well, rather, we're going to accept a function that returns a half, and we're going to name it generate SlopeBlend mask. The reason I'm putting this into a function is because it needs to be reusable. If you're going to do something like displacement, bump mapping, or not bump mapping, but parallel exclusion mapping, or really any effect that requires this mask to be in it, it needs to be regenerated because of the way that data is passed between different shaders. So we're just going to make this reusable code. You can also use it in other effects too, minus the vertex calculations, but that's really up to you. So we're just going to input in here into it. This in is equal to the out of the vertex shader. So up here in the vertex shader, it takes the app to vert G buffer into it, or rather that's the type, and it's taking the in common, which is the in for the vertex shader. As you can see, common Z vertex shader, and then the out of the vertex shader here is then passed to the in of the pixel shader. So common Z past pixel shader, vert to frag Z in. So we're basically passing this in to our function, and then we're going to write our function up here. I created a little commented code block here so that I could keep myself organized. So we're going to name this, we're going to create a function that returns a half. So, and it'll be named generate SlopeBlend mask as before, and we're taking in a vert to frag Z in. So vert to frag Z here is the type. This is or rather it's a struct, really. I mean, it's a type struct. It's weird. It's a little weird. Just to explain it a little bit, this is defining the type that's coming in to the function, and then the in is the actual input. If we actually were going to take this data in and edit it, then we would actually have to also define that we're doing an in-out operation. But we're not, so we're just going to keep this nice and simple. And I think that's the only thing we need for now. So let's create our brackets, and next we need to calculate the vertex normal. So we're going to do this the simplest way that I could think of, since the vertex normal isn't calculated by default, and it's not something that is included in the base vert to frag Z here, the in. We're going to calculate this ourselves. So we're going to name this v normal vertex. Well, let's just stick with v normal. I mean, that makes sense. So our vertex normal is going to be equal to a cross product. So I'm going to put this in brackets. So this math is done first. Let's create another brackets for the cross function. in.vtangent.xyz, and we're going to get the cross product between that and the in.vbinormal.xyz. Okay, then we're going to multiply this by the in.vtangent.w, which is should be the vector length of the vtangent. Okay. This is basically going to normalize everything by the vector length. So we have our vertex normal. Next, we need to, well, first here, let's assign our type here. I always forget to declare the type before typing the variable name. It's just because I work with Python a lot. So next, we're going to need to get just the top facing. So we're going to define another variable, and we're going to call this vnormal We could call it vnormal z, but just for readability, we're going to name it top facing. Is equal to the dot product between v normal and a half 3, 0, 0, 1, because we just want the z-axis, right? So we just want those top facing. And then we're going to return the v normal top facing. Okay, so let me just run over the code real quick. Generate SlopeBlend mask, returns a half. We take in the vertex information from the vertex shader. Output, our vertex normal is calculated, the cross product between in.v_tangent.xyz and in.v_normal.xyz, and then normalized using the in.v_tangent.w. V normal top facing is the dot product between the v normal and half 3 and the z. Okay. Looks good. Naming's all good? Alright. Let's go back down to our section here. So this should generate it, and this should be our out result. So now we're going to take the C albedo, which is already defined way up in the top here of the output albedo and reflectance section. The C albedo comes in as the diffuse map .rgb, so this will be the base diffuse map that you see in the material editor. So basically we're going to override it. We're going to say C albedo is equal to, and let's name this slope mask. So our half slope mask is equal to generate SlopeBlend mask in. So C albedo is equal to slope mask. Okay. Everything's defined correctly. Let's save. And we'll see if we broke anything else. Okay, do I have my... Yes, I got my compiler open. Let's reload the shaders. And look at that. It worked first try. Okay, so now we have the calculation for the top-facing normals. And if you want to actually see what all the vertex normals look like, you can simply, well, not that simply, I guess, but you can change the variable here to half 3. And then we can go to our function, and we basically just output the v-normal instead of the v-normal top-facing. And that will actually show us what all the vertex colors look like, just raw. Oh, I have to change the output to half 3. The reason I'm showing you this is I'm just giving you an idea of how you can debug. Just remember that any data point you input, you can debug by applying as a color. And it's particularly helpful with stuff like this because you can actually see the colors change and get a better general idea of visually what the mathematics represent. And once you've got that, it's a lot easier to work with shaders. Okay, so in the next tutorial, I'm going to cover using this data that we just got and basically modulating it with a height map to break up the blending edges around where the slope blend is calculated, because by default we have this very harsh vertex look, and the lower vertex count you have, the harsher this blend region is going to look. So we're going to want to start from here in the next tutorial, and we're going to go through the threshold, the soft blend part of the shader. So I hope you will join me then. Thanks for watching.